Predicting a continuous value, like house prices, presents a clear analytical path. Yet, the challenge intensifies when the objective shifts from quantifying an outcome to classifying it into distinct categories. For instance, determining if an email is spam or not spam, or if a transaction is fraudulent or legitimate, requires a different statistical framework. Linear regression, effective for continuous predictions, falters fundamentally when faced with these categorical decisions. Applying linear regression to a binary outcome, often coded as 0 or 1, can yield predictions outside this range, producing values like -0.5 or 1.2. These results lack direct interpretability as probabilities, and the model's assumptions about error distribution are violated, leading to unreliable classifications and inefficient parameter estimates. A more robust mechanism is needed to translate features into a probability that precisely aligns with a categorical assignment. This is where logistic regression emerges as a foundational classification algorithm. It addresses the inherent limitations of linear models for categorical prediction by transforming the linear output into a probability, thereby providing a clear basis for classification. Its core utility lies in its ability to model the probability of a binary event occurring based on one or more independent variables. Logistic regression utilizes the logistic function, also known as the sigmoid function, to map any real-valued number into a probability between 0 and 1. This function is critical because it constrains the output to a meaningful range, allowing the model to predict the likelihood of an event belonging to a specific category. This transformation is what differentiates it structurally from linear regression. The sigmoid function, sigma z, is mathematically defined as sigma z equals 1 over 1 plus e caret minus z. Here, z represents the linear combination of the input features and their respective weights, identical to the output of a linear regression equation, z equals beta 0 plus beta 1 x1 plus dots plus beta n xn. The exponential term, e caret z, ensures that the function's output asymptotically approaches 0 as z decreases and 1 as z increases. By passing the linear output z through the sigmoid function, logistic regression compresses the entire range of real numbers into a probability space. A large positive z yields a probability close to 1, indicating a high likelihood of the event, while a large negative z yields a probability near 0, indicating a low likelihood. A z of 0 corresponds to a probability of 0.5. The key distinction from linear regression lies not in the input calculation, but in this final transformation. While linear regression directly outputs z as the predicted value, logistic regression uses z as an exponent in the sigmoid function to produce a probability. This crucial step reorients the model's purpose from magnitude prediction to likelihood estimation. Interpreting the results of logistic regression involves establishing a decision boundary. Typically, if the calculated probability is greater than or equal to 0.5, the observation is classified into one category, for example, 1. If the probability is less than 0.5, it is classified into the other category, 0. This threshold can be adjusted based on the specific application's cost of false positives versus false negatives. This approach is inherently designed for binary outcomes, where there are only two possible classes for the dependent variable. Examples include predicting customer churn, yes/no, loan default, default/no default, or the presence of a disease, present/absent. The model estimates the odds of an observation belonging to the positive class. Real-world applications of logistic regression are extensive. It is widely used in medical diagnosis to predict the likelihood of a disease based on patient symptoms, in finance for credit scoring to assess the probability of loan default, and in marketing for predicting whether a customer will purchase a product. Its simplicity and interpretability contribute to its broad adoption across industries. Training a logistic regression model involves finding the optimal coefficients beta I that maximize the likelihood of observing the actual outcomes given the input data. This optimization is typically performed using iterative methods like gradient descent, which adjusts the coefficients to minimize a cost function, often the log-loss function. The coefficients beta I in logistic regression can be interpreted in terms of log odds. For a continuous predictor x_i, a 1-unit increase in x_i is associated with a beta I increase in the log odds of the outcome being 1. For categorical predictors, the interpretation shifts to the difference in log odds compared to a reference category. Exponentiating the coefficient, beta I, yields the odds ratio, which quantifies how much the odds of the outcome change for a 1-unit increase in the predictor. The decision boundary in logistic regression is not necessarily linear in the original feature space if interaction terms or polynomial features are included. However, in its simplest form with linear combinations of features, the boundary is a straight line or a hyperplane that separates the two classes in the feature space, representing the points where the probability of belonging to either class is 0.5. Despite its effectiveness, logistic regression has limitations. It assumes a linear relationship between the independent variables and the log odds of the dependent variable. It may not perform well with highly complex, nonlinear relationships or when the classes are not linearly separable. In such scenarios, more complex algorithms like support vector machines or neural networks might be more appropriate. Ultimately, logistic regression remains a cornerstone algorithm in machine learning and statistics, providing a powerful and interpretable framework for binary classification problems. Its ability to convert linear predictions into probabilities for categorical assignments makes it an indispensable tool for data analysis.